Good evening, everyone. It's now 5 p.m, so we might make a start. It's now week 10, and we're up to Unit 9, Integration. So for those of you who have been keeping an eye on the schedule given on the course webpage, you may have noticed that we're quite far ahead of schedule. My impression is that there were two main reasons for this. One was that so you would have enough information to complete your assignment. And secondly, so you will have had all of the information required to prepare yourselves for the upcoming quiz. So since all of that's now taken care of, well, since we have now completed the relevant material for both the assignment and the quiz, and now I've got a bit of time left over, I think what we can do is take things a little bit more slowly than what we've been doing, and give ourselves lots of breathing room to fully understand the last few units of this particular course. And so, yes, as always, please feel free to interrupt with questions as soon as you don't understand something. My hope is that we can fill up a lot of the time with questions, discussing things, really getting into the nitty-gritty of what all of this information is that we're going to go through this evening. So I hope that makes sense. And in fact, we might aim to finish a little bit early tonight. We'll see how we go. Okay, Unit 9, Integration. Usually I like to start these units by describing to you why it's so important to study integration. Now, maybe my answer to this is a bit of a cop-out. Fundamentally, at its core, the reason that we study integration is that in a sense, it's the opposite operation to differentiation. So hopefully I've managed to convince you in the last few weeks that it is actually important to find derivatives of things. And if you're convinced that finding derivatives of things is important, then that should convince you that integration is important, because integration is essentially the other side of the coin. So what do I mean by that? Well, at its core, the idea of the derivative is that you're trying to understand what a function is or how a function behaves by looking at its infinitesimal changes. So you pick a point, you look really, really closely at that point and see how much that function is changing, what its slope is. Its slope is meant to give you an idea about how quickly the function is growing at that particular point. Integration is the opposite, in the sense that while derivatives involved breaking things down into little tiny pieces and studying those pieces instead, integration takes all of these tiny pieces, tries to combine them together, hopefully to recover the original function. So what's an actual concrete application of this? Well, I gave you the speedometer example when I was trying to motivate derivatives for you, so I thought I may as well try and use that same example to explain to you why integration is important, or at least explain what you can do with integration. Let's say that you were driving. Let's say you did not have a GPS. You're driving in the middle of nowhere. There are no road signs anywhere. You want to have an idea about how far you've traveled. How would you do this? Well, if you were paying very, very close attention to your speedometer, what you'd be able to do is use your speedometer to work out how far you've traveled. This process is essentially integrating the data given to you by your speedometer. So this is perhaps a naive way of doing this. Now, you might think that this example is obvious, and in some sense, maybe it is. The well-known rule is speed equals distance divided by time. So if you wanted to work out how far you've traveled, if you were going at a constant speed, you'd simply have to work out how fast you were traveling and multiply that by the amount of time that you've been traveling for. So in that sense, that's obvious, but integration is quite powerful in the sense that it allows you to do this even if the speed you're traveling at is not constant. So yes, that's what I consider to be one important example. Now there's another. Well, we're going to go through a lot of important examples this evening. Noticed a pretty outrageous typo here already. We'll go through a few good examples of applications of integration theory this evening, but one really important one that we're not going to treat too concretely yet, but I still want you to be aware of, is the fact that integration theory is essential when you're doing probability theory. So if you want to do anything sensible with data science and statistics in particular, you really need to have a good grasp of all of the theory of integration. So hopefully you're now convinced that this is an important thing to do, and if you're not, maybe you'll become convinced as we go through some more examples this evening. Now, integration. What is this all about? Well, we're actually going to start with a geometric approach to integration. Let's say you've got positive and continuous function that's defined on some closed interval. Defined on some closed interval, and let's say it's going into the positive real numbers. Let's say it just looks like this guy here. Question: what is the area under the curve? Now, this is a fairly interesting question, because if we have a look at this, if we just have a look at the graph, we have some intuitive idea about what the area under the curve should be. Like the concept of area is not a foreign one. We know roughly speaking what area is, but interestingly, one of the first things we need to do in integration theory is define what area actually means. Now, you might think this is a bit bizarre. Sure, I know what the area is. If I look up the word area in the dictionary, it will tell me what it means. But my claim to you is that as mathematicians, we have to make our own definition of area, check that it works out, and check that it's consistent with what our intuition is telling us about the area. So at its core, integration theory is the theory of areas. Now, if you want to construct a general theory of anything, like a general theory of area, you need to have a really good understanding of what the fundamental building blocks of that theory should be. In the case of area, in the case of integration theory, the fundamental building blocks of are rectangles. Now, why do I say that? It's because if I give you a rectangle of height, if I give you a rectangle of length L and height H, you will be able to tell me that the area of this particular rectangle is going to be L times H. This is something that I think lots of people, probably most people in the whole world, would be able to recognize, that this is a good definition of area, at least for rectangles. Now the question is, how do you define areas of other shapes? Well, you're a bit stuck. If you're able to find the length of a rectangle, that means you're allowed to find the area of triangles. You're allowed to find the area of most other polygons, really. But you really, this information, the fact that we know how to find the area of a rectangle, that's not really enough when we're trying to find areas under really weirdly curved things like that. How do you actually define the area under the curve there? This is precisely the question we're hoping to answer this evening. So we know how to find the areas of rectangles. How can we use that to find the area under this curve here? Well, remember, this is just a definition. What we're going to try and do is split the interval up into little sub-intervals. So if we take our function f of x from before, what we're going to do, and we said we're starting at A and we're ending, let's say we end at B. What we're going to do is just pick some numbers in between A and B. Let's pick that, and that. So what I'm going to do is call these x0, x1, x2, x3, x4, and x5. The idea behind finding the area under the curve is to break this up into approximate rectangles, because I know how to find the area of a rectangle. So, you know, if I just look at this interval here, and I pick some midpoint in here, I work out what the function is at that point, and I look at this rectangle here, which is given by the length of this subinterval times the height, which I'm saying is the value of the function at whatever midpoint I chose in there. That should give me a pretty good understanding of what the area under the curve here is. I just say the area under that portion of the curve should be approximately the area of this corresponding rectangle. So this is ultimately what we're going to do. We pick our function, pick a collection of subintervals, pick points on each of those subintervals, we're calling them CI, and then what we're going to do is look at the area of the rectangle corresponding to that partition and the choices of points CI inside all of those subintervals. I know how to find the area of all of those rectangles added up. Now, here's the tricky thing. Here's the conceptually tricky thing here. What I'm going to do is define the area under this curve here by taking limits of this partition as I force the width of all of these intervals to shrink to 0. To make this more precise, I'm going to note the following, that with this collection of rectangles here, the area I've just defined, remembering that I know what the area of a rectangle is, this is going to be the sum, remember our sigma sum notation, from I equals 1 up to n of length, oh no, that's height. Height times length. Because the length of this rectangle is precisely the difference of the points multiplied by the height of the function at whatever midpoint I chose. Basically, the way we define the integral is by simply chucking a limit out the front here and seeing what happens. So this is called the Riemann sum, and the actual area is found by taking limits of the Riemann sum. So with that in mind, we can finally define what area under the curve actually means. Even though we have an idea about the area under the curve, it's not until this point here that we actually have a definition that we can work with as mathematicians and data scientists. So definition. Let's say you've got a positive and continuous function f. The area under this positive and continuous function f is defined to be the limit as n goes to infinity from I equals 1 up to n of f of xi, xi minus 1. Now, what's interesting about this particular definition? Oh, sorry, before I go into that, we can't just take any sequence of partitions here. We have to take a sequence of partitions so that the width of any of the width of the biggest of those subintervals has to be shrinking. Like, right, we're not allowed to just, if we're trying to integrate from A to B, we're not allowed to just choose that as our first partition, choose that as our second partition, and keep doing like that. We need all of the subintervals to shrink to 0. So that would not be an allowable choice of partitions, of a sequence of partitions. And the other interesting thing is that there are actually a lot of ambiguities in this definition. The choice of partition doesn't actually matter. Well, why is this so interesting? Well, the reason I think this is interesting is because, well, whenever you define something, if you're defining the area under the curve, you really want that definition to be independent of the choice of partitions you use. You don't want to choose one sequence of partitions to get one answer and then choose another sequence of partitions and get a different answer. What is so great about this definition, even though we're not going to show it, is that it doesn't matter what sequence of partitions you choose, as long as the width of the biggest subinterval of these partitions does shrink. And the other subtlety associated with this definition is this guy here. Now, this is what we call a right endpoint approximation, because we've defined the length of the interval, the rectangles we're dealing with, we've defined them to be the length of the subinterval multiplied by the height of the function at the rightmost endpoint. But in principle, we could actually choose any point in between that interval, and we should still get the same answer. And in fact, we do. And so I'm going to say we could replace this with any number ci inside this interval here. This is another interesting thing where you're allowed to play around with your choice of intermediate point in your approximation, and your answer is still going to be the same. All of these facts I'm not going to prove to you because they are a bit tricky, but this is quite nice, and this is the definition of the area under the curve. Now, any questions at this point? All right, I might move on then, but please feel free to interrupt whenever. Okay, now this was the area under the curve, and yet this is a unit in integration theory. So let's get on with the integration. Okay. Now, for integration, we can define integration for any continuous function. Now, and as before, we define, if you've got a continuous function that goes in the closed interval a, b up to r, we're going to define the integral of this function to be the limit of these Riemann sums. And as before, we still need the length of maximal subinterval interval to vanish. So, same as before, we take our Riemann sum approximations from before, we take a limit, and this is supposed to give us our integral. We denote this integral with f of x dx. Sorry, we've got this integral sign from a up to b, f of x dx. Now, question for you to see if you've been paying attention. What is the difference between the Riemann integral and the area under the curve? What's different about these definitions, apart from the obvious different symbols? What is the difference between my definition of the Riemann integral and the definition of area underneath the curve? No one knows what the difference is. Okay, so I tried to make this easy for you by emphasizing this word any, putting this word any in italics. From before, when we were dealing with area under the curve, in order to really make sense of area underneath the curve, we really needed that function to be positive, whereas this definition of Riemann integral works for any continuous function. It doesn't necessarily need to be positive. Even though for area under the curve, technically we need the function to be positive, the integral can be defined for any function. It's allowed to change signs. So we'll talk about that in a second, but one more thing I want to point out about this definition before we talk about the relationship between the integral and area under the curve, is this f of x dx thing. This can be some cause of confusion, but hopefully it won't cause too much confusion. This x in the f of x dx expression, this is a dummy variable. It's not actual. This x doesn't have any technical function. It's just there to make this expression look a bit more aesthetically pleasing. What I mean by that is that, if you replace f of u, if you replace x with u, then this is the exact same expression. Because if you're integrating a function, the only pieces of information you need, if you're taking the Riemann integral of a function, the only pieces of information you need are the function itself, as well as the two endpoints that you're integrating between. Your choice of variable doesn't really make any difference except for those aesthetic differences. So I hope that's clear. Now back to our discussion on the difference between area under the curve and the Riemann integral. If you've got a continuous function f and you're finding its Riemann integral, if that function f happens to be positive, the Riemann integral is going to be exactly the same as the area underneath the curve. But in case the function f changes sign, you get something a bit different. What do I mean by that? Well, what I said in these slides here, if your function is not positive on your integral, then it doesn't really make any sense to say that the integral is the area under the curve. Instead, what's going on is it gives you a signed area. So what do I mean by that? Well, let's zoom in a bit here. If you've got a function that's changing signs a bit, and let's say this is b and this is a here, what's going on here? Well, on this part of the graph, your function is positive. And so you do get your usual notion of the area under the curve. On the other hand, if you're on this part of the interval, then your function is negative. But hopefully you can still see that just by flipping the graph, you can again define the area underneath the curve. And that area underneath the curve would be this stuff over here. And then same thing over here, you'll get an area under the curve that comes from positive contributions of the graph. So this area is a positive number, this area is a positive number, this area is a positive number, but when you integrate, the contributions of these areas are actually given signs depending on whether they're above or below the x-axis. So this is what's going on here. If you integrate a function that does change sign, what you're going to end up with is the area above the x-axis minus the area below the x-axis. Sorry, the area below the graph and above the x-axis, and you've got to subtract the area that's below the x-axis but above the graph. So this is what integration means. It's not always area, it's assigned area, depending on whether the area contributions are above or below the x-axis. Any questions on that? We'll get into some application, we'll get into some questions about finding area underneath the curve soon enough. But maybe the first thing we should, do after having defined area and the Riemann integral is give you access to one of the best tools in mathematics. It's used all the time. People don't even notice it, but it'll be good for you to notice it. And this is the idea of antiderivatives and the fundamental theorem of calculus. So I told you that integration is in some sense the opposite of differentiation. It's the information in this slide which will hopefully convince you why that is true. So before we get into that, I've got to give you a definition which I think makes fairly intuitive sense. Let's say you've got a continuous function on some closed interval. An antiderivative for that function is a function which is the which is the antiderivative of f, in the sense that we know how to differentiate. And if we differentiate this antiderivative, we should get back to the original function itself. So if you think of taking a function and differentiating, finding the antiderivative is doing the opposite. Now, I claim to you that integration is actually the thing that achieves this. So why would I introduce integration when antiderivative already has its own well-defined term? And the reason, of course, is the fundamental theorem of calculus. You may have heard of this before. It's fundamental because it is actually used all the time. In fact, it's used so much that quite often people won't even reference the fact that they're using it because it's so well known and it's so well celebrated. So this theorem basically answers the question, what does integration have to do with finding antiderivatives? And the answer is this. Let's say you've got a continuous function f that goes from a closed interval into the real numbers. Then I'm going to define a new function. This gets a bit tricky. The new function I have is going to be a of x. It's defined to be the Riemann integral of this function f. Now, when I take a Riemann integral, I need to specify what my bounds are. My lower bound is going to be a, the leftmost point on this closed interval. The upper bound is not going to be b. Instead, it's going to be x. So I need x to be somewhere here because I'm saying that this function depends on x. So I'm going to put the x there. So what does that mean? So it means that I've got a continuous function. Let's say a is there and b is there. This function a of x, what does it do? It finds the point x. It closes off the interval there, and it basically finds the area under the curve there, or the integral more generally. So we've got, looks like I've missed a couple of comments. Yes, Xiaowang, this is exactly what it's doing. A of x finds the area from the leftmost point of the function all the way up to x. So as x travels from a to b, you'll get more area or less area depending on whether your function is positive or negative. So of course, the point of this theorem is not just the definition of this function, it's the observation that this function is actually an antiderivative for f. This is pretty exciting stuff. So I've got a good picture of this on the next slide, but just before we get to that, I need to elaborate a bit more on what this means. Now, question for you: how unique are antiderivatives? If I give you a function and I ask you to find an antiderivative, and you give me one, how many more are there going to be other than the one you just gave me? This is hopefully just a revision question from last time. Please put your answers in the chat if you feel like you can. So I've got some comments. Yes, good answers here. In fact, yes, there are infinitely many. There certainly are infinitely many. But I like the final comments. I think we need an initial argument like x of 0. That is more or less the answer. The answer are there are infinitely many, and in fact, you get a different, if you take an antiderivative, you can get a new one simply by adding a constant function onto that. Because remember, by the mean value theorem, constants are the only functions that have zero derivatives. So they're the only thing you can add onto an antiderivative to not change the derivative. So this means that since we've found an antiderivative, that means that any other antiderivative has to look like that plus some constant. So if I give you a function and I asked you to find the antiderivative, you could just write down this expression and technically you'd be correct. It's that expression plus c. And this is what the last part of the fundamental theorem of calculus is seeking to address. If I ask you for a function, if I give you a continuous function small f, and you give me an antiderivative capital F, then my claim to you is that I know exactly what antiderivative you picked. Well, almost. I almost know what antiderivative you picked. I can't write it down exactly, but I know that if I take your antiderivative that you gave me, and I look at f of b minus f of a, then it should equal this particular integral here. So this is the role of antiderivatives and integrals. Now this particular equation here is going to be something we'll see a lot in this course. And so as a last part of this theorem, I'm actually going to give you some notation. Instead of writing f of b minus f of a, we're going to simplify that a bit because we're going to be using it so much. Instead of writing all of this clunky expression here, I might write this. F of x vertical line, superscript b, subscript a. That means evaluate f of x for x equals b. Well, actually, no, there's not really anything else I can write there. F of x for x equals b, subtract f of x for x equals a. This is one that I've seen a lot. I think this one is also acceptable, though I've seen it less frequently. So this is that. Now, I've got a whole slide dedicated to a great picture I saw from Wikipedia, of course, which really explains the fundamental theorem of calculus and why it's true. So remember, the fundamental theorem of calculus said that this function a of x, which is equal to the integral, so let's put a here and let's put b up here. The integral from a up to x of f of x, oh no, can't use x, f of t dt, this function is an antiderivative for the function f. What does that actually mean? It means that the derivative of a is actually equal to the original function itself. Let's see why this is true. Well, remember how we defined the derivative? We had to look at the limit as h approaches 0. So let's just remind ourselves what we're actually evaluating here. The derivative of a at a point x is equal to the limit as h approaches 0 of the integral from, well, actually, I'll do it in a few more steps. A of x plus h minus a of x minus a of x plus h minus a of x divided by h. But remember, this is equal to the integral from a up to x plus h of f of t dt minus the same integral except up to only x this time, divided by h. Now, this leftmost guy here, I might actually just put that down a tiny bit. The integral of f of t dt from a all the way up to x plus h. Well, if this is a, this is x, and this is x plus h, then this integral here is meant to be capturing all of the area underneath this curve here. In particular, it gets both the red and the blue bits. However, this integral here, it's minus the integral from a up to x of f of t dt. A all the way up to X, that's only capturing this blue area here. So we've got blue plus red minus blue. That's exactly this red area here. Now, the area, this red area here, it looks like a rectangle, doesn't it? Well, if H is small enough, this is starting to look like a good rectangle. And the area of this rectangle is going to be the length of the base, which we've said is H, multiplied by its height, which is approximately f of x. And so this excess area that Wikipedia is telling us about, this is about f of x times h. So that means that this is approximately f of x times h divided by h, and this is going to be going to f of x. So this is the fundamental theorem of calculus illustrated. We can nicely think about this in terms of areas underneath the curve. Please speak up if that didn't make any sense, because this is probably the last good picture we'll see for quite a while. I'll just give a brief pause for a moment. All right, I'll keep moving on. I hope that was clear, but please speak up if that wasn't. We're now going to get into properties of the integral. So we should be very familiar with these kinds of theorems by now. We've seen them for limits, we've seen them for derivatives. Now we're going to see these for integrals. So the setting is, let's take two continuous functions f and g defined on some closed interval. The left point of this interval is a, and the right point of this interval is b. It's going into the real numbers. We're also going to let c be a real number. Now, even though I've introduced f, g, and c, the first of these, the first property of the integral that we're going to discuss actually only involves a single function. And it says the following: the integral of f of x dx from b up to a is the same as minus the integral from a up to b f of x dx. Now, I think in the course reader this was stated as a theorem, but really this is a definition. Why? Well, the fact is that we haven't made any sense of this. We've only defined integrals where the subscript is lower than the superscript. We haven't really made any sense of this. So when I say that the integral from b of a of f of x dx is equal to minus the integral from a up to b of f of x dx, this is really a definition. It's just really saying that if you swap your numbers around and you reverse your orientation, then that should reverse the sign of your area. So that's really what's going on here. We've got an interesting comment here, that f of b minus f of a is equal to minus f of a minus f of b. Zhao, I wondered if you could give us some context for that statement there. I mean, it's certainly true, but maybe you could elaborate on why you say that. Well, it's an interesting formula to bring up. I'm thinking that maybe you had. No, that's okay. I mean, I guess maybe you're thinking of this particular formula here, and you suggest this can make sense. This makes sense even if b is less than a, and to some extent that's true. But you still run into the same problem as before in that this is only defined, while you can define this when b is less than a, we still haven't defined this if B is less than A. But of course, you're right. You can think about it either of these ways. And the fact is that I think this is a definition. In fact, it's the only way you can define it so that you do get that nice identity that you were describing there. So maybe you think this is all getting a bit technical, and maybe you're right. So we'll move on to the next one. This is an interesting one because this is an example where you don't actually need the theory of integration to find the area underneath the curve. So the situation here is that you've got x and you've got f of x, but for us, sorry, let's not call it that. Let's have a look at this function here, which is just constant. What is the area underneath this curve here? Well, obviously, the answer is C times B minus A. Now, while you may think this is obvious, the fact that this is also true for the integral is actually some sort of validation for us, because the fact that the integral from A up to B of C dx is exactly equal to what we would expect the area underneath the rectangle is, this gives us validation that our theory of integration is doing what we want it to do. Because remember, we wanted the theory of integration to be generalizing, finding the areas of rectangles. And so in particular, if we integrate a rectangle, we should get the usual area that we're familiar with. And indeed we do, so that's nice. Okay, we have the usual sum thing. So in words, you know what's going to come here. Integral of sums is the sum of integrals. And the same thing is true for subtraction as well. So I think that's fairly intuitively clear why that should be the case. Another fun one is that if you integrate not just the function f, but some scalar multiple of that function, then you're going to just get the integral of that function scaled. And I guess that makes a lot of sense. If you're trying to find the area underneath this curve and you scale it, that's probably a bit too extreme. Then the area under this should be, well, let's say you multiplied by 2, getting from here to here, then the area under this should be about twice, should be exactly twice the area underneath that. Okay, now the next one, let's say that you're integrating the function f of x from a up to b, and let's say that you happen to pick a midpoint c in between that integral. Let's say your function looks like this. Then the area under this plus the area under this should be the same as the total area. So this is another good validation of our theory of areas, that if you've got two shapes, the area of both of those shapes should be the same as the area of one shape plus the area of the other shape. Now, I've actually got maybe a tricky question for you. This is true if C lies between A and B. Is it also true if C lies outside of that interval? Don't think so? Any other suggestions? Anyone else want to say yes? Anyone else want to say no? So I've got no, I don't think so. I've also got one person saying true. Yes, this is actually true, even if C is not in the interval. And the reason is because as soon as, well, it's because of our sign flipping convention from before. as soon as we take c out here, the signs flip. I won't get too much into it, but everything works out precisely because of this this definition here. So yeah, so as you move it outside, you start getting like signed areas, flipping signs, but everything works out, and this still remains true. Final one, perhaps the easy one. If you integrate the function f from a up to a, you're going to get 0. Now, again, this is really a definition. I mean, you could try and say, well, it has to be this way because of the fundamental theorem of calculus. But again, more fundamentally, the reason we say that the integral from a up to a is 0 is because if you got your function a up to b, and this is your point, and this is your point here, there's no area there. A single line does not have any area, and so that's why we really think we have to define the integral from f of x dx from a up to a is equal to 0. Okay, so we've got a request for some more elaboration on this one here. So I'm certainly happy to provide that. Lewis, could you perhaps explain what in particular about it you don't understand, or is it just the whole concept and you want me to do it all over again? Oh, sorry. I mean, sorry if that's not how you wanted this. I guess the idea is that if you're dealing with a function that's constant, then the area underneath the curve is just a rectangle. The height of this is exactly c, and the length of it is going to be b minus a, because that's the length of this part down here. And so it has to be, those are the dimensions of this rectangle. And so our theory of integration, in order for it to be the same as the usual area, the integral of this function has to be the same as the area of the rectangle, which is base times height. The height is c, and the length of the base is b minus a. Okay, cool. Thanks for your question. Now, we've got a lot of good theory under our belts, but we haven't really done any examples yet. We've defined area underneath the curve. We've defined integrals. We've seen properties of the integral. It's now time to apply this to some real functions. So the first one is a bit of an interesting one. Let's have a look at the function ln of x. We know, well, we originally defined the logarithm to be the inverse of the exponential function, but it turns out that there is another pretty fun way of defining it. You can define the logarithm, the natural logarithm, as the area under the curve of the function 1 on t for t between 1 and x. So 1 and x. Let's try and graph the function 1 on t. F of t equals 1 on t. The logarithm of x is precisely this area underneath this curve here. So that's quite nice. And this is true for all positive x. Now, I know, well, just reminding everyone that if x is less than 1, if x is down here, we've got to find we've still got to find the area underneath the curve, but we've got to give it a minus sign because of that theorem we saw before. But this makes sense, because if x is less than 1, we know that the logarithm is negative, so it all still works out. So let's get on with this. How might we do this? Well, I guess the thing is that in some sense, the answer becomes obvious once you have access to the fundamental theorem of calculus, because you know what the derivative of the logarithm function is. You know that the derivative of log of x is exactly 1 divided by x. So to make this a bit more precise, let's consider a new function which measures how much the logarithm of x fails to be the same as the integral from 1 up to x of 1 on t dt. Ultimately, what we want to show is that g of x is equal to 0. So we want to show that g of x equals 0 for all x greater than 0. Okay, how do we show that a function is 0? Well, if we're using tools from calculus, we know that if the function happens to be 0 at some point and happens to have a 0 derivative everywhere, then it has to be 0 everywhere, because the only functions with vanishing derivatives everywhere are constant. So, oh, we've hit our 50 mark. Look, you know what? I might pause it there. You can think about this question a bit more yourselves, and I'll leave it for 10 minutes, and I'll be back with you at 6 p.m. Hope you have a good 10 minutes. See you soon. Hello again, everyone. So before we get back into to this question, I wanted to point out to you to address a problem that came up last time, and that was the question of how does one communicate in the chat using integrals. One recommendation I can give you is to just use this sort of notation that I'm just about to put in the chat. So if you want to ask me a question on the chat and your question requires you to input integrals, then that is my preferred way of doing it, because that's how you put it in LaTeX, and I'm able to read that quite quickly. So yes, that's an answer to that problem that came up before. Okay, back to this question. We were trying to show that the natural logarithm of x could actually be expressed as the integral from 1 up to x of 1 on t dt. And so what we're going to do, we're considering the function g of x. We want to show that function is going to be 0. Now, I'm going to start by just differentiating this function, g dash of x. Well, I know that the logarithm of x is an antiderivative of 1 on x. In particular, that the derivative of log of x is 1 on x. And by the fundamental theorem of calculus, I know that this function has a derivative, and its derivative is precisely whatever was in the inside. So g prime of x equals 1 divided by x minus 1 divided by x. And of course, this is equal to 0. And just remembering that we're dealing with x bigger than 0 here. Okay, that's great. That means that the derivative of g vanishes everywhere. So that means this function g is constant. Therefore, g is constant in x. Now what we have to do is work out what this constant is. So since this function is constant, it suffices to know what it is at a particular point. And the particular point we're going to look at is the point 1, of course. So g of x has to be equal to g of 1 for all x. But g of 1, by definition, is equal to the natural logarithm of 1 minus the integral from 1 up to 1 of 1 on the integral from 1 up to 1 of 1 on t dt. This is 0 because the exponential of 0 is 1, and logarithm was defined to be the inverse of the exponential function. And this, well, by design, is equal to 0. So this now shows that there's a fun way of describing the natural logarithm function. You can think of the natural logarithm function as an area function. So that's quite nice. Now we'll move on to some more concrete examples. Evaluate the integral from 0 up to pi on 2 of sine of x dx. Now I think this is a pretty natural question to ask, because the sine function that we're dealing with, we know roughly what it looks like. We know that it has a peak at pi on 2, it goes back to 0 at pi, and then so on. What this question is asking us to do is work out what this area under the curve is. So even though this looks like a pretty hideous symbol, really what we're trying to do is trying to find something really geometric, namely just this whole area underneath here. And the tool we're going to use to do this is the fundamental theorem of calculus. In order to apply the fundamental theorem of calculus, we need an antiderivative of the sine of x function. Do we all remember what an antiderivative of the sine of x function is? Maybe just quickly snap it in the chat if you feel like it. Yep, minus cosine, good work. So minus cosine is an antiderivative for the sine function. And so we now have all the ingredients we need to apply the fundamental theorem of calculus. We've identified our antiderivative. And so the fundamental theorem of calculus says, remember, this is going to be f of pi on 2 minus f of 0, where capital F is any antiderivative of the function. We've suggested that an antiderivative is minus cosine of x, so all we need to do is evaluate minus cosine of x at pi on 2 and subtract whatever minus cosine is at 0. Well, minus cosine of pi on 2, that is equal to 0, because remember the cosine function starts at 1 and hits 0 at pi on 2. That's 0, and this is minus 1, because cosine of 0 is 1, minus cosine of 0 is minus 1, and minus of that is 1 again. So this is pretty nice, because even though the sine function is a bit foreign in the sense that you can't really express it in terms of polynomials, at least not a finite number of polynomials. And it's saying that this area in here is exactly equal to 1, even though we're integrating a weird function from 0 up to an even weirder number, pi on 2. So I think this is a pretty cute result. All right. Now, another one. Let's define the function capital F of u to be equal to the integral from 2 up to u of 1 on the square root of 1 plus t squared dt. This one, I don't think we should sweat about too much. I think this is a particularly easy question. It's just a straight out application of the fundamental theorem of calculus. The fundamental theorem of calculus tells us that if we want to differentiate this, all we need to do is take this and replace all of the t's with u's. So we get the derivative of this function is 1 divided by the square root of 1 plus u squared. Now the reason we included such a simple function is because of what comes next. We're going to be stepping it up a bit. Let's consider the function g of x is equal to the integral. So it's the same, we're integrating the same function as before, except instead of integrating up to x, we're integrating up to the sine of x. And I want you to find the derivative. Now, as I said, this question is a step up. Not only do we have to apply the fundamental theorem of calculus, but there is another theorem that we have to apply in order to evaluate this derivative. Question for the audience. Put your answer in the chat if you can. What is the other theorem we need in order to answer this question? What other piece of calculus machinery do we need access to? Chain rule. Yes, that is absolutely correct. We need the chain rule. And the reason for that is because we can express this as a chain function. We can write f of x, we can write that capital G of x is the same as f of sine of x, where f is the question we had last time. So remember, we defined f of u to be equal to the integral from 2 up to u dt on the square root of 1 plus t squared. And so f of sine of x equals the integral from 2 up to sine of x dt on the square root of 1 plus t squared. But this is precisely the question whose derivative we're trying to find. So we now have the fact that g of x is equal to f of sine of x. So the chain rule tells us that we can exactly work out the derivative, provided we know what the derivative of f is, and provided we know what the derivative of sine is. But we were really clever because we already did the derivative of f. That's exactly what we did in the last question. Because, well, I'll backpedal a bit. We said that the derivative of f was equal to 1 on the square root of 1 plus whatever the input variable is. This time, the input variable is sine of x. So the derivative of g is equal to the derivative of f evaluated at sine of x multiplied by the cosine function. This cosine function just goes exactly there. And remember, the derivative of f is 1 divided by the square root of 1 plus whatever the input was. The input was sine of x, so sine of x goes exactly there. So this is that question there. The derivative of g is cosine of x divided by 1 plus the sine of x squared. So this is a good question because it combines the use of both the fundamental theorem of calculus and the chain rule in a way that we haven't really seen before. Okay. Next question. This one is a bit more of a geometric one. Finds the area between the x-axis and the curve y equals sine of x for 0 between x and pi. Now, you can probably already guess what the answer is. If this is the sine of x function, then we know that it starts at 0, peaks at pi on 2, and ends at pi, and it peaks at the value 1. We just said that the area here was equal to 1, and so by symmetry, we really would expect that the integral of the whole thing, the area under the whole curve, would be 2. But nevertheless, I'll do it the full way, just to give you guys practice with using the fundamental theorem of calculus. So it's the exact same thing we already saw. We have to find an antiderivative. We've said an antiderivative is minus cosine of x. We have to evaluate that derivative at pi and subtract the evaluation of that antiderivative at 0. We end up with 2. So this is exactly what you'd expect. Now on to a slightly trickier area underneath the curve question, one we haven't really looked at before. Finds the area bounded by the two curves y equals x squared and y equals y cubed on the interval 0 up to 1. So let me try and give you a graph of what's going on here. Both the x squared and the x cubed functions, they start at 0 and end at 1. But for numbers less than 1, the cube function makes them even smaller. So while the x squared function looks like this, the x cubed function looks even flatter. Well, let's say it's something like that. Try and find the area between these two curves. Now, this is sort of a tricky question because I've only really defined area under the curve. I haven't really told you how to find areas between two curves. But perhaps your intuition is telling you that's the way you should do this. Well, actually, maybe this can be another question for the audience. How would you find the area between two curves like this? What is the geometric way we could do this? Yes, thank you for that, Yingjian. So that is exactly right. The idea is that we should be able to find the area under the whole x squared thing, and then just remove whatever area we had from under the x cubed thing. So in terms of the notation and the symbols that we've been using, what we're really asking you to find here is the integral from 0 up to 1 of x squared minus x cubed dx. So this is all this question is asking. So we may as well get on with the computation. I guess the first thing we need to do is point out exactly what I did, that on this interval, the x squared function does actually dominate. That tells us which one we should be subtracting from what. So the integral, this is equal to the integral from 0 up to 1 of x squared minus x cubed dx. I've already used one of the properties of the integral to break it up, because remember, the difference of integrals is the integral of the difference. And so we end up with this. And these two integrals we can just do separately. There is a typo here. I'm not raising 0 to the power of 1. Rather, I wanted that 0 to be a subscript there. In any case, in order to integrate x squared, I need an antiderivative. X cubed on 3 is an antiderivative for x squared. And so that integral is x cubed on 3 evaluated at 1, subtracts that same evaluation at 0. On the other hand, an antiderivative for x cubed is x to the 4 on 4. And again, we have to evaluate that between 1 and 0. We end up with a third minus a quarter, and that ends up just being exactly a 12th. Now, the very last thing I'll do in this subsection 9.1 is something that maybe you could argue I should have done immediately after discussing the theorem. The reason I didn't do that is because I wanted to get on to examples. But nevertheless, the corollary is this. If you've got a non-negative and continuous function on the closed interval from a up to b, then the integral from a up to b of f of x dx is greater than or equal to 0. Now, this is yet another one of these corollaries which you may think is like stupidly obvious. Why would I even need to bring attention to this fact? Well, one of the things that's coming to my mind at the moment is that even though we defined the integral initially to be the area underneath the curve, at least in the case that the function was non-negative and continuous, we never explicitly stated that areas have to be non-negative. And it is actually obvious from the definition of the integral that areas underneath the curve of a positive function do have to be non-negative. It's actually also very easy to see that this is true from the fundamental theorem of calculus. Because, I'll explain why. If you define f of x to be equal to the integral from a up to x of f of t dt, then a prime of x, this is a non-negative function. Because we said that the original function f was non-negative. So therefore the derivative of a is non-negative, but the mean value theorem tells us that if the function a has non-negative derivative, then it actually has to be increasing, or at least it can't be decreasing. So since a of a is equal to 0, we find that a of b has to be greater than or equal to 0. We've got a function that starts at 0 and has positive or at least non-negative derivative, and so it has to finish at a non-negative number. So maybe you think that this is a completely stupid thing to bring up, but one of the reasons I pointed this out is to demonstrate to you that there are usually a number of different ways of approaching sorts of problems. Okay, so that was 9.1. I'll leave a brief amount of time for any comments or questions that you may have. Yep. Right, I might make a move on to section 9.2, approximate integration. So this is an interesting topic because the way we defined the integral was by taking limits. we took a continuous function, we did a partition of the interval, and we defined the integral to be, well, we found the approximate area of this particular partition, and we took limits as this partition shrunk so that all of the individual subintervals shrunk to 0. In practice, at least in terms of putting things on a computer, more often than not, your computer cannot do this for you. You cannot tell a computer to compute infinitely many approximations of your area, and you can't tell it to take a limit, at least not generally. In some special cases you can, just because it happens to know the answer ahead of time. But in general, you can't do it. And so in practice, you have to settle for only doing the approximation. So what does this mean practically? Well, if you're given a continuous function and you're asked to evaluate the integral of that function from on the interval a up to b, if f is complicated enough, you're not going to be able to do it. However, you can provide a pretty good answer by exactly computing the Riemann sum. So you would define a partition and you would say that, well, the area under the curve is approximately equal to this particular sum here. So a picture of what's going on, if you've got your x and y axes here, and you've got your function f of x, then you would construct a partition and you would evaluate the function at the left endpoints of each interval. And you would define an approximate area to be the corresponding the areas of the corresponding rectangles all added up. So you take the leftmost point of each interval and carry that across and say, well, the area under the curve should approximately be that, plus that, plus that. This is called the left endpoint approximation for the integral because the heights of the rectangles you choose come precisely from the left points of the interval. Of course, you can do the same thing for the right endpoint approximations as well. And another way which provides the average of the two, this is when you don't actually necessarily choose the height of your rectangle to be the height of any particular point on the... Oh, sorry, you do that. No, the thing is that you choose the heights of your rectangles to be exactly halfway between the height of the left point and the height of the rightmost point. And this is referred to as the trapezoidal rule for approximate integration. We've got another question. Isn't Taylor a choice? I presume you're talking about some sort of Taylor approximation to integration. Perhaps you could elaborate on that, Kai? Oh, I see. I see. So what you're suggesting is that another way to do approximate integration is to take the Taylor series for f of x and then cut that Taylor series off somewhere and just integrate that because that's a polynomial, and so therefore you know how to integrate it. Yes, that is certainly one way to integrate. The biggest problem with that suggestion, however, is that you quite often want to find integrals of functions that do not have Taylor series. So, for example, let's say you were trying to integrate a fractal or Brownian motion. Brownian motion is another good way to think of it, because Brownian motion is not differentiable anywhere. It doesn't have a Taylor series, and yet you still might want. It is conceivable that you'd need to integrate Brownian motion for whatever reason. So I suppose that if you have access to a Taylor series, then in general, doing your method is a good idea. But in full generality, we could be integrating something as bad as an arbitrary continuous function, including this Brownian motion. And so unfortunately, in full generality, we need slightly more broad tools that we have access to that will allow us to do this approximate integration. Hope that makes sense. Okay, so this is actually all that was in section 9.2, just pointing out different ways that you might be called on to use different methods that you have access to when you're called upon in the future to do integrals that you don't know how to do explicitly. So of course, all of these approximations can be done up pretty easily using mathematical or any other software, any other coding language software that you're using. Okay, so we're going to move away from, we're going to move slightly away from thinking about integrals as areas and look at integrals as a more abstract object. And we're going to start looking at these things called indefinite integrals. What does this mean? Well, notation-wise, it just means you say the integral of f of x dx, and you don't specify an upper bound and you don't specify a lower bound. What does this mean? Well, I'm going to say that this means if you just write the integral of f of x dx without specifying any upper or lower bounds, what that means is simply the set of all antiderivatives of that function f. And remember, once you've found one antiderivative, you've found all of them, you just need to add a constant. So another way of seeing this is to say the following: if you manage to find some antiderivative capital F for your function small of f, then the integral of f of x, the indefinite integral of f of x, is equal to capital F of x plus c for any real number c. Now we've actually done a bit of this already when we were trying to solve differential equations. We had to integrate certain functions, include extra constants, and then sort out what those constants were later. So because this is a fairly standard thing to do, finding indefinite integrals and finding these antiderivatives, I thought that one thing, well, it might be handy for you to have access to a table which gives you a lot of the most common antiderivatives. So we've got this table here. So what's going on here? This is just saying that if you've got some small function f, what should its antiderivative be? Well, let's say to start off with, we have a function small f, and we happen to know an antiderivative. Then if we multiply the original function small f by a constant, then an antiderivative for that new function is the old antiderivative multiplied by that same constant. And of course, if you add up functions, then the corresponding antiderivative can be found simply by adding up those functions. But really what's interesting, what you might find useful, is access to all of these. These are some nice functions and their corresponding antiderivatives. So if, for example, you're given x to the power of alpha and you're asked to integrate that, find the indefinite integral, or you're asked to find the antiderivative, you know that the answer is going to be x to the power of alpha plus 1 divided by alpha plus 1. Because by our differentiate, we can quite easily verify using our differentiation rules that the derivative of this is exactly that. Sine and cosine we're quite familiar with. This is a slightly more tricky one. Sec squared. Remember, sec squared sec is equal to 1 divided by cosine, I believe. Yeah, that's right. 1 divided by cosine. So the integral of sec squared is actually the tangent function. The antiderivative of e to the x is also e to the x. And you may remember that back here, we needed alpha to not be minus 1. What happens if it was minus 1? Well, then that's the same as integrating 1 on x, and we know that the answer is log of x. Technically speaking, this is only true for positive x. But remember, even though these tables are useful, when you're asked to find the set of all antiderivatives, that means you have to add arbitrary constants to all of these antiderivatives you see in this table. Okay, now let's have a look at a question that will hopefully illustrate what I mean by finding antiderivatives and indefinite integrals. Question: you're given a function x squared plus 3 of x, finds the indefinite integral of x squared plus 3x dx. And recall what that means is I want you to find all possible antiderivatives of this function here. Well, remember the sum of antiderivatives. If you've got the sum of two functions and you know what antiderivatives for those functions are individually, then that means that you can add the corresponding antiderivatives up to get a new antiderivative. We know that an antiderivative for x squared is x cubed on 3. We know that an antiderivative for 3x is 3x squared on 2, but we need to remember our plus c's because there are more than one answer. There's more than one answer to this question. Actually, there are infinitely many answers to this question, and they're described in terms of these constants, plus c. Now, another example, except this one's not actually defined in terms of integrals. We've got a function, and we're told that its second derivative is x minus the square root of x. Find the original function f of x. I guess the only thing that's slightly tricky about this particular question is that we have to do the indefinite integral twice in order to do this. Now, before we start, it's good to keep this in mind. Since we're integrating twice, it means that we're going to have two constants floating around here. We get one constant each time we do the integral. All right, well, we've got to integrate once. The integral of x is x squared on 2. An integral for root x, you just have to shift the power up by 1 and then divide by the inverse of that. So it's 2 times x to the 3 on 2 on 3 plus c. So we've found what the first derivative is. And then we just have to integrate once more to find, well, an antiderivative for x squared on 2 is x cubed on 6. An antiderivative for 2 times x to the power of 3 on 2 divided by 3 is 4 times x to the power of 5 on 2 on 15. If we're given c, then an antiderivative for c is cx, and we need one more constant because of that integration we did. Since we had to undo two derivatives, that means that there were going to be two constants floating around there. All right, so that was basically all we wanted to look at for section 9.3, which was indefinite integrals. Now, now that we've done some examples of some simple integrals, ones where we simply could just look at the table to tell us what the answer was, we're now going to have a look at explicitly evaluating some much more tricky integrals. But before we do that, it's handy to get some tools in our arsenal that we can use to evaluate these tricky integrals. So in this section, I just want to run you through a couple of standard tricks that one should know when considering integration theory. So what have we got? Now, a lot of these techniques are not really tricks per se. They're just the integral version of a few theorems that we saw for derivatives. So, for example, the first integration trick I'm going to teach you is basically just the integral version of the chain rule. So the chain rule is a theorem that concerns how you can differentiate chains of functions. This technique that I'm about to introduce to you is basically just the reverse of that. And it's called integration by substitution. So let's suppose that for whatever reason, you wanted to find the antiderivative, the indefinite integral of a function that looks like this. The function was f of g of x times g prime of x dx. So let's say we had this thing to integrate, we could explicitly work out what f and g are. Then, by the chain rule, roughly speaking, that's the same as this, basically just a consequence of the chain rule. And this is just going to be the indefinite integral of that. Now, I certainly appreciate that this equation doesn't really make good sense at the moment. The best I can do to alleviate that worry that you might have is by promising that we'll do some examples soon to explain exactly what I mean by this. This So yeah, so what I'm saying here is, I'm just going to call this bad. This is bad manners. While intuitively it makes sense what this means, writing this equation doesn't make me feel all that comfortable because it doesn't really make much sense. This equation, on the other hand, does make a lot of sense. This makes perfect sense. If you happen to have, again, let's say we're trying to integrate this, except this time we know explicitly upper bounds and lower bounds, then this integral can be expressed as the integral from g of a up to g of b of f of u du. So integration by substitution is basically just the opposite of the chain rule. Chain rule tells you how to differentiate chains of functions. Integration by substitution tells you how to undo that process. So let's have a look at an example. Now, you may remember that in the previous slide, I said that in order to use integration by substitution, you had to have an integral of the form f of g of x times g prime of x. In exams, assignments, and real life in general, you're never going to be told exactly what those functions are. Instead, you've got to work it out for yourself. So, question. Finds the indefinite integral of x cubed cosine of x to the 4 plus 2, and we're integrating with respect to x. How do we do this one? Well, this happened immediately after I described to you integration by substitution, so there's a good chance we're going to have to find a substitution. And indeed, that is the case. And our substitution is as follows. The reason this works, well, I'm going to set u to be equal to x to the 4 plus 2. Why would I do that? Well, cosine of x to the 4 plus 2, like that's a pretty tricky thing to integrate straight out. So I'm just going to let x to the 4 plus 2 be its own thing. Now, the reason I can get away with this is because the derivative of u is equal to 4x cubed. And x cubed is precisely what we've got here. So x cubed is equal to 1/4 du on dx. So that means that this integral here is exactly equal to, well, cosine of u times x cubed dx, but x cubed dx is exactly du on 4. So now I'm just trying to find the integral of cosine of u on 4. That is a much, much more manageable task because I know an antiderivative of cosine of u, it's going to be sine of u. So the integral of cosine of u on 4 is exactly the integral of sine of u on 4. But remember, we've got to include our plus c constants. And also, it's good manners to write your final answer in terms of the variables that you were originally presented with in the first place. The question was presented in terms of x, and so we shouldn't really leave our answer in terms of u. Remember, u was x to the 4th plus 2. So the final answer is going to be sine of x to the 4 plus 2 on 4 plus c, and c is any real number. So that was that example. Another good one that we'll come across is I want you to find the integral of 5x minus 3 to the power of minus 2, and it's not an indefinite integral. This time, we're going to integrate from 1 up to 2. How does this go down? Well, integration by substitution again. Probably the most natural thing to do is to introduce the function g of x, which is 5x minus 3, and note that the derivative of g of x is equal to 5. So when we do integration by substitution, what happens? Well, we started with this integral. By the theorem of integration by substitution, I know that this integral is the same as the integral of this, the integral of 1 on 5u squared from g1 up to g2. So this 5 came from here, and this u squared came from the fact that what we're doing to 5x minus 3 in this integral is we're squaring it. But once that's out of the way, we can actually just proceed as usual because we know how to deal with this antiderivative. G of 1 is equal to 2. G of 2 is equal to 7. So I'll just quickly write that out. G of 1 is equal to 5 times 1 minus 3 is equal to 2. And G of 2 is equal to 5 times 2 minus 3, which is equal to 7. So now all I need to do is find the integral of 1 on u squared from 2 up to 7, and I'm dividing that all by 5. Using the standard tricks we had from before, we end up with 1/14. So we do expect to get an actual number as an answer to this question, because we're essentially asked to find a definite integral, which we can think of as area under the curve. We're trying to find an area between two points, 1 and 2, and so we expect that the answer should actually be a number. Any questions on this so far? We've got a few more of these examples, but I thought we might take a quick pause here to see if anyone had any questions. Yep, thanks, Xiaowang. All right, let's move on to the next one. The next one's a pretty interesting one. Finds the indefinite integral of 1 on the square root of a squared minus x squared for any positive a. This is a very tricky one, and I would not blame you if you could not work this out off the top of your head. The substitution that's best to make here is actually the following. And no, I wouldn't have been able to come up with this by myself if I didn't know ahead of time what it was. Define x to be a of sine theta. Why would I do this? Well, dx divided by d theta is equal to a of cosine of theta, and so that means when I rearrange, I get this particular equation there. What happens next? Well, we're going to do our integration by substitution. With this substitution, the function 1 on the square root of a squared minus x squared becomes, well, 1 on the square root of a squared minus x squared is equal to the square root, 1 on the square root of a squared minus a squared sine squared theta. So that's this term there, but the a cosine theta comes from that. How do we proceed from there? Well, we've got a squared here on both of these terms, so we actually just pull it out the front. The square root of a squared is just a. This is true, remember, because a is positive. So we then see that these a's cancel, and the square root of 1 minus sine squared of theta, that's exactly equal to, well, the square root of 1 minus sine squared of theta is just cosine of theta. These cosine of thetas cancel. We end up with just the integral of d theta, which of course is just theta plus some constant. But remember, theta was defined so that x is equal to a times sine of theta. So that means theta is equal to x divided by, sine of theta is equal to x divided by a, and theta equals the arc sine of that. So this is that particular example here. It's a pretty tricky one, but yes, this is how you deal with annoying terms on the bottom like that. The square root of a squared minus x squared. Now, the next example we're going to do is another trigonometric one. Finds the integral of cosine of x, sine of x. Now, we actually, the correct way to do this question is to let u be sine of x. Why would you do that? Yes, I am missing a dx here. Thank you for that observation. So we're going to let u be sine of x. The reason we do that is that du on dx is exactly cosine of x, and we've already got that there. So that means if we're doing integration by substitution, this integral is exactly going to be u, the integral of u du. We know how to integrate u. That's just u squared on 2 plus our arbitrary constant from before. But remember, u is defined to be sine of x. So we get sine squared of x on 2 plus c. Another fairly straightforward one there, I hope. We'll do one more example of this before we have another 10-minute break, I think. The last one is this one here. Find the integral of 3x plus 1 times 3x squared plus 2x raised to the power of 3. I think what the most sensible thing to do here is define u to be 3x squared plus 2x, because then the derivative, it's equal to 6x plus 2, but this is just some scalar multiple of that. So this is a good sign that this is a correct choice of substitution there. So we define u to be equal to 3x squared plus 2x as I suggested, find the derivative. What this means is that 3x plus 1, this term here, is exactly equal to a half du on dx. So then this becomes half du on dx. This just becomes u cubed, and the dx is cancelled, and we end up with this, the integral of u cubed on 2 du. That ends up being u to the power of 4 on 8, because the antiderivative for u cubed is u to the 4th on 4. 4 times 2 is 8. We've got to include our arbitrary constant from before, and we also have to remember how we originally defined u. We defined u to be 3x squared plus 2x. So u to the 4th is 3x squared plus 2x raised to the power of 4. And we've got the 8th out the front from before. So this was a few examples of use of integration by substitution. As I suggested, it's basically just the opposite of the chain rule. So integration to substitution is to integration what the chain rule is to differentiation. I'll leave it there for 10 minutes. We'll have our break, and then we'll come back at 7 p.m. Hope you enjoy your 10-minute break, and I'll see you shortly. Hello again, everyone. Now back for the final installment of this evening's lecture, and we'll continue with our explicit integration techniques, part of Unit 9. Well, we'll see how far through we get with this, and I expect we'll probably aim to end the lecture 10 or 15 minutes early if we can manage that. So let's keep going. We've just spent a lot of time discussing how integration by substitution, which I claimed was basically the integral opposite of the chain rule, could be used to solve certain integrals. Now we're going to be looking at the opposite of the product rule. So the product rule is a certain rule for differentiation. The next technique we're going to be talking about is basically the integral version of that, and this is called integration by parts. This is a very well-known technique. So to set the scene, consider the following. Say you've got two functions u and v. We know that the derivative of the product of those two is exactly equal to the derivative of the first multiplied by the second plus the first multiplied by the derivative of the second. Integration by parts basically just falls out by integrating both sides of this equation. If you integrate the left-hand side, you get exactly uv. On the other hand, if you integrate the left-hand side, you get the integral of u. Sorry, give me a second. I lost my pen. There it is. So yes, if you integrate both sides of this equation, you get uv equals the integral of u dash v plus the integral of uv dash. And so if you rearrange this equation, you get precisely this expression here. Now, you might be thinking, what on earth is the point of integration by parts? You just replace one derivative with another. The reason for integration by parts is basically if you can work out that your integrand, what's inside your integral sign, is a product of something, so that if you put the derivative of one on the other side, you really want that new integral to be manageable. So really what this means is if for whatever reason you happen to have an integral that looks like this, and it so happens that if you put the derivative that was originally on v, if you put that derivative on u instead, if this guy is actually a manageable integral, then you might want to consider doing integration by parts. Most of the classic examples of integration by parts, or at least the utility of integration by parts, these arise when you're dealing with products of polynomials with log functions, products of polynomials with trigonometric functions. So let's have a look at an example. The example I'm going to give you is x cubed times the logarithm of x. So what I'm going to do is I'm going to let u be equal to the logarithm of x, and I'm going to let v dash be equal to x cubed, because then this integral is exactly u times v dash, and remember, integration by parts tells me that this is exactly equal to uv minus the integral of u dash times v. And the hope is that this integral is easier to deal with. Why would that be the case? Well, the derivative of u is just 1 on x, whereas the antiderivative of v dash is just going to be some other polynomial. So what we're going to have is just some polynomial in here, and hopefully we know how to do that. So this is roughly how we want this to go down. Let's set this up a bit more carefully. Define the function u to be log of x. Define the function v to be x to the fourth on 4, so that v dash is actually equal to x cubed, that guy there. And u is log x, so the derivative of u is 1 divided by x. This is quite helpful because this derivative that we're trying to work out, this is exactly equal to the integral of u v dash. And so this is equal to uv minus the integral of u dash v. So u dash is 1 on x and v is x to the fourth on 4. Now, x to the fourth on 4 log x, that just comes down. Whereas if we take the 1 on 4 out of the front of this integral and cancel one of the powers of x with the 4 on top, we get x cubed dx dx. I don't know why I've got 2 dx's there. Now, again, the x to the fourth on 4 log x just comes out the front, while the integral of x cubed, we know an antiderivative for x cubed is x to the fourth on 4. That 4 combines with this 4 to give 16, and we're just left with some arbitrary constant as usual. So that's a pretty classical example of the use of integration by parts. You replace one derivative with you replace one integral with 2 terms. The first of these doesn't have an integral at all, and the second of these is an integral which hopefully you can solve using other techniques. Another good example is when you're multiplying polynomials by the exponential function. How do you evaluate the derivative, the integral of that? Well, this time I'm going to set u to be equal to x, and I'm going to set v to be equal to e to the x. Why do that? Well, because the derivative of u is 1 and the derivative of v is e to the x. So that means this integral is exactly equal to u times v dash. It's also equal to u times v, but for the purposes of integration by parts, I really want a v dash here. And remember, this is just equal to uv minus the integral of u dash v. Why would that be helpful? Well, u dash times v is just 1 times e to the x, and that's a particularly easy thing to integrate. As I said before, this is equal to the integral of uv dash. This is equal to let me write this properly, uv, and this is the integral of u dash v. X e to the x, well, the integral of e to the x is just e to the x, so it ends up with x times e to the x minus e to the x, which I can factor nicely like that. And then I've got to include my arbitrary constants from before. So this is another good example of integration by parts. Now, this is basically, these are the only 2 examples of integration by parts we'll look at. Before we move on, is there anything anyone wants to say on anything? All right, let's move on. Now, I want to spend a bit of time on a particular function whose antiderivative we've actually seen a few times, but there's something else we can do. So the function I'm dealing with is the natural logarithm function. The natural logarithm function is defined for all positive x, and we know that the derivative of log of x is 1 on x. So the derivative of the log function is 1 on x, but this is only true for positive x. Now, despite the fact that this only makes sense for positive x, this expression here should make sense for all all x not equal to 0. The integral of 1 on x should still make sense even if x is a negative number. So what is the antiderivative in that case? Well, let's start with what we know. We know that the integral of 1 on x is equal to the natural logarithm of x for positive x. In order to flip the sign, we're going to use the chain rule again. If x is less than or equal to 0, then we can talk about the natural logarithm of minus x, because now minus x is positive. And the derivative of the natural logarithm of minus x is, well, use the chain rule. It's the derivative of the logarithm of minus x times the derivative of minus x with dx. Well, remember the derivative of logarithm is 1 divided by whatever's inside, and the derivative of minus x is obviously minus 1. So this is also equal to 1 divided by x. So this is yet another function whose derivative is 1 on x, except this time the domain of the function is x strictly less than 0. So that means that the integral of this is log of x if x is positive, and the integral of this is log of minus x if x is negative. Basically, the way we summarize that is by saying that the antiderivative of the function 1 divided by x is equal to the natural logarithm of the absolute value of x plus an arbitrary constant c. So this is how you define the antiderivative of 1 on x, even on domains where x could be negative. So this is a useful thing to know. So that was that. One more explicit integration technique that might be good to go through is, it's a technique that concerns integration of ratios of polynomials. It's very straightforward to integrate polynomials, but it's a bit more tricky to integrate polynomials divided by other polynomials. So I'll now give you some rough techniques that can be used to deal with this. So this general technique is called integration by partial fractions. It concerns when you have a denominator, you're trying to integrate something with a denominator, and the denominator is a bit annoying. So you try and replace that denominator with other things which are less annoying. So to make this concrete, let's suppose we've got a function f of x, which is equal to the ratio of two polynomials, p and q. Now, roughly speaking, what happens is that in order to do integration by partial fractions, you really need to factorize the denominator, and you need to factorize it into products of polynomials that are either quadratics or linear terms. Once you've done that, roughly speaking, what goes on is you try and write this fraction here as a sum of other fractions, and the denominators of all of these new fractions are these same factors of q that we just found. Now, of course, this is very abstract. Let's try and give a concrete example of what I mean by this. Let's suppose that you were given let's suppose you were given real numbers a, b, c, and d, and you wanted to integrate the function cx plus d divided by x minus a times x minus b. What you want to do is write this fraction as a sum of two other fractions. These fractions are going to be ratios of polynomials, but the important thing is that what's on the denominator, they're just these same terms. And the idea then is to try and find what these capital A and B numbers are, because once you've done this, these integrals are much easier to find. They're just going to be logarithms. So this is roughly speaking how integration by partial fractions goes down. Let's have a look at an actual concrete example of this. The integral of x plus 2 dx on x squared plus x. Well, as I suggested, the way to do this is to really the first thing you need to do is factorize the bottom, factorize the denominator. Well, x squared plus x is equal to x of x plus 1. So this tells me that the two factors I should have when I split my fraction up into the sum of two other fractions, there should be x and x plus 1. So what I'm going to say is I'm going to be looking for a decomposition of this fraction here into the sum of two terms. I'm just going to have just some numbers on the top. On the bottom, I'm going to have these two factors I already had. Now, the tricky question is, what are these numbers a and b? This is the part that's trickiest, I think. What should these a and b numbers be? Well, the way to do that is by combining these two fractions so they look like this one. So the way you do that is multiply top and bottom by x plus 1 on this fraction, and you multiply top and bottom of this fraction by x. Because when you do that, this becomes a of x plus 1 plus bx divided by x plus 1x. Of course, this is equal to a of x plus 1. Actually, I'll simplify that a bit differently. This is going to be x of a plus b, x a plus b plus a, divided by x squared plus x. So what I really want, I want these two numbers a and b chosen so that this fraction is the same as this fraction here. Well, if I do that, what I end up with is the following. As I suggested before, what we end up, if I simplify this, what ends up happening is I get that x squared plus 2, x of a plus b plus a on x squared plus x. This should equal that fraction there. Since the denominators are the same, that means that the numerators also need to be the same. So this means that x squared plus 2 is equal to x. Oh, there's not supposed to be a squared there. X plus 2 should be the same as x of a plus b plus a. So I need this to be the same as this. And this has to be true for all x. If I set x equals to 0, what I'm going to find is that a is equal to 2. And if I set x to be basically any other number, what I'm going to find is that a plus b, it has to be the same coefficient as what's in front of here, 1. A equals 2 and a plus b equals 1, so b is equal to minus 1. What this means is that this thing that I'm trying to integrate, this is exactly equal to 2 on x plus minus 1 divided by x plus 1. The great thing about partial fractions, the reason I did this is because I know how to integrate both of those two functions. So how does this go down? As I said before, you split the fraction up like this. You're trying to find these two integrals here. I know exactly what these integrals are now. The integral of 2 on x is 2 times the logarithm of the absolute value of x. The integral of 1 on x plus 1, well, that's just the logarithm of the absolute value of x plus 1. So I used a bit of the chain rule there. And finally, you need to include your constants. We've got one more question that concerns integration by partial fractions, and I think after we've done this, I might leave it for the evening. So the last example we'll do this evening is this one here. Finds the indefinite integral, the set of all antiderivatives of the function dx divided by x squared minus a squared. We want a to not be 0. Okay. Now, as I suggested before, the way we do these sorts of questions is by factoring the denominator. Difference of 2 squareds. This is pretty easy to factorize. And so the idea what we really want here, we want to say that 1 on x squared minus a squared, we want to express this as some fraction whose only denominator is x plus a, and some fraction whose only denominator is x minus a. So if we do that, if we assume this, what's going to happen? Well, this is just what I wrote before. I want 1 on x squared minus a squared to look like this, a on x plus a plus b on x minus a. I now need to work out what these numbers a and b are. Well, if I multiply top and bottom of this first fraction by x minus a, and multiply top and bottom of this fraction by x plus a, I combine the two fractions, combine the top and bottom. What I end up with is this expression here. And I need a plus b times x to be equal to, well, there's no x terms here, so I need a plus b to be equal to 0. And I also need a minus b to be equal to minus 1. So we may see that we've got almost these exact same computations occurring in the chat at the same time, so that's good. As was suggested, a plus b needs to be equal to 0, and a minus b needs to be equal to minus 1 on a. System of two linear simultaneous equations. I'm hoping that you're familiar with how one would actually solve these equations simultaneously. I won't go in the details, too far into the details now. If we do this, we get that a is equal to minus 1 on 2a. And we also find that b is equal to 1 on 2a. So this gives us the numbers that we need. I'm now in a position to integrate because I now know that 1 on x squared minus a squared is equal to a minus 1 on 2a x plus a plus b, which I said is 1 on 2a x minus a. I know how to integrate both of these functions. So I'm in a good position to answer the question now. As I said, these are the two functions we're trying to integrate. I know how to integrate them. We just got the logarithm of absolute values again. Logarithm of the absolute value of x minus a, and the logarithm of the and the logarithm of the absolute value of x plus a. Got factors of 2a that have come out the front. And as usual, I have my plus c. Okay, since we've been making good progress on the content recently, and because this seems like a fairly natural place to stop, I think I'm happy to end the lecture there. Because we are leaving early, I'm happy to stick around and answer questions you may have on the content. But I think this is where I'll stop with the content. And I'll stop recording now. So thank you everyone for your attention this evening.